So welcome, everyone. It's a great pleasure tonight to welcome Gordon Belot to New York University, Abu Dhabi. Gordon received his PhD from the University of Pittsburgh, where he wrote a dissertation on the interpretation of classical and quantum gravity. He has taught at Princeton University, New York University, New York, the University of Pittsburgh, and the University of Michigan, where he is currently professor of philosophy and member of the Michigan Center for Theoretical Physics. Among his honors and awards, Gordon has held fellowships from the National Science Foundation, the Center for Advanced Studies in Behavioral Sciences at Stanford University, and the Burkhardt Fellowship from the American Council of Learned Societies. He also has the potentially dubious honor of having been my dissertation advisor. Gordon has published widely in the Foundations of Physics, including a recent book, Geometric Possibility, published in 2001 by Oxford University Press, and an edited anthology entitled Spacetime. Much of Gordon's work has focused on the status and representation of space and time within physics, general relativity in particular, the concepts of background independence and general covariance, and the status of physical and mathematical symmetries within foundational physical theories. His work has been published in the British Journal for the Philosophy of Science, Studies in History and Philosophy of Modern Physics, and General Relativity and Gravitation, among other places. More recently, Gordon's work has turned to broader issues in the methodology and philosophy of science, in particular, the use of mathematical and statistical frameworks for modeling scientific reasoning. Recent work on Bayesian confirmation theory and the notion of statistical typicality has been published in the journals Philosophy of Science and Statistics and Probability Letters. Tonight, he'll be speaking to us about this more recent work and how it relates to a set of puzzles concerning the roles that bias and background assumptions play in the inferences that we draw from new information. Please join me in welcoming Gordon Belot.
Thanks very much. So it's a very great pleasure to be back in New York and to be here. And, the slides are live. So here's a sort of outline which you may be able to read. I think in a way every philosophy talk is an introductory lecture. And the reason why I say that will become clear in a minute or two. So I'm going to start this lecture the way I start a lot of introductory lectures by talking about what I think philosophy is. But the view I have about what philosophy is has been encapsulated much better than I could ever do by Bertrand Russell in an interview late in his life. I think he was about 90 when he gave this interview. So I'm going to try to play a film clip from the interview that puts across the picture of philosophy that I want to talk about tonight.
Lord Russell, what is philosophy?
Well, that's a very controversial question. I think no two philosophers will give you the same answer. My own view would be that philosophy consists of speculations about matters where exact knowledge is not yet possible. But that will only be my answer, not anybody else's.
What's the difference between philosophy and science?
Well, roughly you would say science is what we know and philosophy is what we don't know. That's a simple definition. And for that reason, Christians are perpetually passing over from philosophy into science as knowledge advances.
When something is established and discovered, it ceases to be philosophy and becomes science.
Yes. And all sorts of questions that used to be labeled philosophy are no longer so labeled.
What good is philosophy?
All right. Well, we'll come back at the end to Russell's answer to that question beyond his sigh of despair. I think the basic picture he has is right. Philosophy is the subject that's concerned with those fundamental questions that aren't the concern of some other field. So basically, all fundamental questions start out being part of philosophy. And those on which progress becomes possible, rapid, sustained, permanent progress becomes possible, become part of other fields. So in ancient times, mathematics and astronomy split off from philosophy. Physics split off sometime in the 17th century. Biology maybe around the same time or maybe a little later. Psychology in the 19th century. Computer science you can think of as initially concerned with a bunch of problems that had been part of philosophy, but once progress became possible, they became their own very successful discipline. So when Russell says science is what we know and philosophy is what we don't know, he means those questions on which progress has become possible have been assigned to the other departments and removed from the realm of philosophy just because progress became possible. So what does that mean? It means philosophy is eternally left with just the intractable fundamental problems. Okay, so that's what I'm going to talk about, an intractable fundamental problem tonight that's been with us since the beginning of philosophy, and it is not yet migrated into some other discipline because progress has remained so elusive about this question. So I'm going to talk about this problem in terms of preconceptions. What sort of preconceptions is it okay to have when you try to approach some empirical question, and which kinds of preconceptions should you avoid? But there are lots of other ways of getting into this problem, but I think this is a nice, quick way. So let's think a little bit about a couple of examples from the sciences in which preconceptions stood in the way of scientific progress. So here's a picture of the sun covered in sunspots. I take it it's not unusual at all for the sun to display this many sunspots. Of course, it's hard for us to see the sun except under special conditions or using special equipment normally. But even with the naked eye, you can sometimes see sunspots on the sun. For instance, if it's obscured by a cloud of smoke. So there's this sort of puzzle about the history of the understanding of this phenomenon. In China, reports about sunspots date back more than 2,200 years. And west of China, you can find reports of sunspots, for instance, in historical chronicles. So here's a passage from a Russian historian writing, I think, in the 12th century, describing a terrible period in which you could tell terrible things were going on because spots appeared on the sun, and that caused fires. Okay? In fact, almost certainly it was the other way around. There were massive forest fires in Eastern Europe that created the kinds of conditions under which you could just see the sunspots that are almost always there. Okay, but here's the puzzle. Within the history, the tradition of astronomy that began in ancient Greece and traced through the Arabic world and the Latin West, sunspots were not reported by astronomers until the beginning of the 17th century when telescopic observations of the sun became possible. So the puzzle is what was going on west of China. And the answer that most historians of science seem to accept is that within that tradition, the tradition that descends from the Greeks, it was believed that the heavens were eternal and changeless and that the sun was perfect. So it wouldn't make any sense for there to be sunspots moving across the face of the sun. And people saw what they expected to see. Okay, so indeed, the sort of exception that proves the rule, there were a number of very famous astronomers who reported seeing black spots on the sun, but they interpreted them as seeing Venus moving across the sun. And in particular, they never reported having seen more than one of them at a time. So that sort of picture we started with many sunspots on the face of the sun at one time, is a picture that never came up in this history of astronomy until the 17th century. So it seems like people saw what they expected to see. They had certain preconceptions about what the world was like, and that shaped the kind of investigations that they carried out and the kind of observations that they reported. Another quicker example of the same general kind, until 50 years ago, primatology, the study of primates, was dominated by men. And just as an empirical fact, it seems that the men who were in the field tended to pay attention to adult female langurs, for instance, in this example, mostly when they were interacting with children or with adult males. And they didn't pay that much attention to them when they were having social interactions between each other. And not wholly surprisingly, when more women came into this field, more observations were made on adult female langurs, and a different picture of the social interactions and social structures of langur groups started to emerge. Okay, so here we have another sort of more subtle case where people's preconceptions shaped what they saw. Right? They sort of stood in the way of noticing certain things about the world. They expected the world to be one way, and they didn't really notice that it wasn't because that expectation was an obstacle to learning about the world. So just in general, sort of a big picture fact is we all want to find out about the truth. Right? And some preconceptions, and here I'm using preconception in a sort of very broad way, so it could either be a belief about the way the world is, like that the sun is perfect, or a methodological preconception, that you only have to look at certain kinds of phenomena if you want to find out about how the world works. Some preconceptions frustrate our desire to get to the truth. We all want to be objective. We all want to be free of those preconceptions that obstruct our search for truth. So I think this is a widely shared goal, at least, especially among scientists. So that was the sort of entry into the problem I want to talk about tonight. And most of what I want to say is in the next two sections. The first topic is sort of, is it possible for us to just live without preconceptions? If it is, that seems like that would be best. Then we would be sure that we didn't have preconceptions that were standing in the way of our desire to get to the truth. I'll argue that we can't. And then we get to the hard part. Right? If we can't live without preconceptions, then we have to have some. How do we draw the line between those that are acceptable and those that aren't acceptable? How do we draw the line between the ones that are going to obstruct our desire to get to the truth and the ones that are harmless? Okay, so let's start with life without preconceptions. Okay, so what does it mean to be objective? Which preconceptions do we need to avoid? Well, a natural first idea is that we should just avoid all preconceptions, right? These are like, why would you think, wouldn't it be great if we could just look at the evidence and decide what to believe without having that process be shaped in any way by the beliefs we arrived at the lab with, for instance? Right? That seems like the ideal. Zero preconceptions. Now we know we're being objective, right? The only way we can fail to be objective is to have preconceptions that obstruct our desire to get to the truth. So if we have no preconceptions at all, everything will be fine. So there's this notion of absolute objectivity, that we should begin inquiry, say in a lab, but more generally any kind of inquiry where we're trying to find out about the world, without making any substantive assumptions about how the world works. That would be great if this would work, if we could be absolutely objective. Okay, but it seems like confusing. As soon as you write this down, you think like, okay, suppose I wanted to find out about Ebola. Like, what's the first thing I should do? I mean, you might think I should go get a microscope, right? But if I'm really approaching this problem with no preconceptions at all, it's hard to say why I should use a microscope instead of, say, a telescope. Unfortunately, the stars don't show up too well in this picture. Right? So why I want to find out about Ebola, but I'm approaching the problem with no substantive views at all about what the world's like. Why look at little things instead of really big things? Or indeed, something like, why not look at through a kaleidoscope, right? Like, why use one instrument or toy rather than another, right? We all know there are good answers, good reasons why you should use the microscope. But that's only because whenever we approach one of these problems, we really do have some substantive beliefs about the world in the first place. Okay, but that seems a little too quick as a way of dismissing the idea of absolute objectivity, right? The idea isn't that like every day when you go to the lab, you don't have any beliefs about how the world works. It's that somehow you started out, or we started out, with zero beliefs about what the world were like, and sort of built up our knowledge about the world till it got to the point where when somebody asked us a question about, say, Ebola, we reached for the microscope. We started out as blank slates, but now we've progressed far enough that we have good reasons for using a microscope. Okay, so here's a quote that philosophers like to trot out at this point in their lectures. It's from an old economist, A.B. Wolfe, and I think we like it just because he states so clearly this picture that it would be great if we could start out as blank slates and build our way up from there. So he says, if we try to imagine how a mind of superhuman power and reach would use the scientific method, the process would be as follows. First, all facts would be observed and recorded without selection or a priori guess as to their relative importance. Right? We're blank slates. Nature hands us the facts. We just record them. Then, the observed and recorded facts would be analyzed, compared, and classified without hypothesis or postulates other than those necessarily evolved in the logic of thought. Right? So in these first two steps, no preconceptions. Right? Just the facts. Just the facts, first of all recorded and then organized, but without supposing anything in particular about how the world works. Third step, from analysis of the facts, generalizations would be inductively drawn as to the relations classificatory or causal between them. And then there's a fourth one, deriving predictions, basically, from the things we arrived at the third stage. Okay, so I think this is the most sort of explicit way of describing what an absolutely objective procedure would look like. Now, remember the first stage was collecting all of the facts without, thanks very much. Collecting all of the facts without having any preconceptions or making any presuppositions about what the world is like. And I mean, if you think about this, of course, it's impossible to do that. Right? The first step in inquiry cannot be collect all the facts before you do anything else, just because there are infinitely many facts. Right? I mean, we think within this room there's an electromagnetic field, right? That's responsible for everything you see, right? You making measurements of the electromagnetic field. Well, it's characterized by different values at different points of space. And there are infinitely many points of space in the room, let's say. So in order to collect all the facts, first of all, you'd have to know everything about the electromagnetic field in this room, and that's already infinitely many facts. Then you'd have to know everything about, say, the average temperature in the universe at every instant of time from the Big Bang until now. Well, that's also an infinite number of facts, and so on. There's no way you could ever carry out this procedure that Wolfe was describing. You could not start by listing all the facts and then move on to the second stage, because you would never complete the first stage. And of course, actual scientific inquiry doesn't require the first stage to ever be completed. Why? Well, you only have to record the important facts, or the ones you're interested in, or the ones that seem like they might be relevant later. But the only way that you can make those distinctions is by starting out with some substantive ideas about what the world's like. Okay, the second stage can also never be completed. At the second stage, you were supposed to, having the complete list of all the facts in front of you, you were supposed to list all of the patterns that you found among the facts. But the problem here is that each thing, take these three things, okay, naively, this one's more similar to that one than it is to this one. Right? But if I started to list all of the facts I could about those three objects, I would end up finding just as many ways that these two were similar and that those two were similar. If you want to, during the question period, we can play this game. I can tell you, I will win by listing a lot of really boring similarities and dissimilarities. And you'll say, but those are uninteresting. And I'll totally agree. But the point is that when we actually analyze data in science, we only pay attention to interesting patterns and not to boring ones, because we have substantive ideas about how the world works. We know how to make that distinction between interesting and boring. But that's just to say we're not being absolutely objective. The third stage is also impossible. At the third stage, you're supposed to reason inductively. So you're supposed to say things like, well, you know, I've looked at the epidemiology papers, and I can see that there's this big correlation between smoking and cancer. So I think that will hold up in the future. If I go and do more studies, I'll find further correlations between smoking and cancer. The thing is, we can only do that sort of thing because we think some of the correlations in the data are relevant and some are spurious. If we seriously thought that every correlation that we found in the data would continue in the future, we'd end up making contradictory predictions. Okay, so here's a sort of silly way of making the point that philosophers like. Statisticians probably have much more sophisticated ways of doing it. So think about all the emeralds that have been dug up so far in the history of the world. They've all been green. I hope that's true. I don't really know about emeralds. Let's say it is. Okay, all the emeralds so far have been green. So reasoning inductively, we expect the emeralds dug up next year to be green. Okay, that's good. I believe that. I think that's the right thing to believe. But say I'm trying to approach this problem with no preconceptions about what the world's like. Right? Then I should notice that in addition to being green, all of the emeralds that have been dug up so far also have this other funny property. This would be a lot more clear if we spoke German, because then it would just be one word. They are blue or mined before 2016. Right? Every single emerald we've ever dug up so far has been either blue or mined before 2016. Right? It's just a little trick. Right? They've all been mined before 2016, so they've been blue or mined before 2016. Okay? But if I'm seriously going to expect every correlation in the data to hold in the future, then I should expect the emeralds that are dug up next year to be blue or mined before 2016. So I expect them to be green, of course, and now I also expect them, the ones next year, to be blue or mined before 2016. Okay? But the ones dug up next year aren't going to be mined before 2016. So if I really expect them to be blue or mined before 2016, I expect them to be blue. So if I really expect all of the patterns in the data to carry over into the future, I expect next year's emeralds to be both blue and green. Of course I don't. Sorry. Of course I don't. But that's because I think green is the kind of property you use to make predictions. And this funny made-up one is not. Okay? The point is, in order to carry out this third stage, you have to make that kind of distinction too. Right? You have to have substantive ideas about what the world is like if you're going to learn anything at all, is the lesson of this slide. So the idea that we could get by entirely without preconceptions is unfortunately just a fantasy. It's a beautiful idea, but it turns out when you look at it more carefully that it's actually impossible for several reasons, because we're finite beings, but also for logical reasons that have to do with that last thing that we just talked about. Okay, so I think that means that we shouldn't be afraid of having preconceptions. We want to learn about the world. We've just seen that if you want to learn about the world, you've got to have some preconceptions. So let's embrace that. Let's say, yes, it's okay to have some preconceptions about what the world is like even before you start your experiments. It's unavoidable. So we can't get by without them. So we need some way of differentiating between the unacceptable and the acceptable preconceptions. Those ones that are going to frustrate our desire to get to the truth and the others. So which ones are bad? Right? What kind of situation could we be in where we could say, yeah, that's a really bad preconception. You shouldn't have that one, because it's going to inhibit you from being able to learn. Well, one way that could happen, and I'm sure you can all think of people you know who have this problem, is if they have some belief about the world that's insulated from evidence. Right? They believe this thing, and they're going to keep believing it no matter what evidence they see. Right? That's something that really happens. Here's a sort of toy example. Right? So say I start out life convinced that space is tiger infested. And I just hold on to that belief no matter what. Right? Now maybe you started out thinking that was likely. Like we were raised in a community where people just thought space was full of tigers. Right? But I was certain of it. right? So any evidence you show me, like any part of space where there's no tigers, I just think, that shows they're all in that other part of space today. Whereas you become more and more dubious that space is tiger infested over time. You're capable of learning, but I'm not, because I'm absolutely certain. And I protect this belief from any kind of refutation. Okay. That's a disaster for me. I've got a preconception that's preventing me from learning about the world. We want to avoid those ones. Those are the worst case scenarios. Okay, so here's a suggestion. This particular formulation of it is from a colleague of mine, but the basic idea that underlies this you can find in all kinds of writings by scientists and philosophers. So what he says, Peterelton here, all rational participants will, as evidence becomes complete, tend to converge to determinate true conclusions on all non-vague, unambiguous questions. Once the evidence is in, there'll be no room for variable or subjective determination of conclusions among rational participants. So the idea is, if you've got some kind of preconception that prevents you from reaching agreement with your peers as more and more evidence comes in, then it's bad, right? You're not learning about the world, you're just, your beliefs depend on and reflect just your starting point. Right? If everybody else is converging to a certain view as they see more and more evidence and you're just refusing to, then you've got this kind of, you're failing to be objective in the kind of way that we want to avoid. Right? And you can think back to those examples I gave at the beginning, they didn't have this feature. As a matter of fact, their expectation that the sun should be perfect inhibited astronomers west of China from noticing sunspots for a long time. But in the end, they did notice them. And if there had been more communication between Chinese astronomers and others, then they probably could have just shown them, look, here, look at the sun through this piece of cloudy glass, and you'll see there's something weird going on that you didn't expect. Right? The preconceptions of the Greek astronomers and their intellectual descendants inhibited them from noticing this phenomenon, but it didn't totally prevent it. And the same thing with the primatology example. Right? Primatology progress was slowed down a little while at worst by the fact that there were so few women in the field. When women came into the field, they said, no, look, there's this stuff you guys weren't noticing, and agreement, consensus about that emerged pretty soon, although there was a little bit of friction. These are good cases, right? Happy endings, where people had preconceptions that were shaping their investigations. But those preconceptions washed out as more and more evidence came in. That's the situation we all want to be in. We can't live without preconceptions, but let's try to make sure that whatever preconceptions we have, they wash out when the evidence comes in so that we'll all be able to converge to the truth in the end, no matter where we started. So that's a basic idea that I think a lot of people find really attractive, and I do too. And now I'm going to try to convince you that this one won't work either. I mean, this is why this problem is intractable. Right? You come up with what seems to you like the best possible route to solving it, and then it always turns out that there's problems. So we want to avoid these worst case scenarios. So here's a definition and a proposal. The definition says, a method for addressing a problem is convergently objective, if and only if applying the method is virtually guaranteed to lead to beliefs that converge to the truth as more and more evidence accumulates. Okay, so I'll give a couple of examples that illustrate this idea in a second. But the basic idea is you've got this method for finding out about the world, and it's a good one just in case, as you see more and more evidence, your beliefs about the thing you're interested in get closer and closer to the truth. And my proposal is, that I'm going to try to talk you into right now and then talk you out of in 10 or 15 minutes, is that if our method is objective in this sense, then we should believe what it says about the world. And if it's not objective in this sense, then we shouldn't. Okay, so I think this is like really intuitive picture, right? That the good methods are the ones that will lead you to the truth, no matter which thing is true. If you've got one of those, then yeah, you should endorse its outputs, right? if you just stick with that plan, you will end up with beliefs closer and closer to the truth. If you've got some method that lacks that feature, then you know there are circumstances under which your beliefs just aren't going to track the truth. Right? And so what you end up believing after you see a bunch of evidence will just reflect your starting point rather than the evidence that you're seeing. Right? That's the intuition behind this proposal. I think it's a very strong one. So I think the proposal is really plausible. It's been endorsed all over the place by a lot of people. I want to consider the consequences of following through on this proposal if we consider some very, very simple kinds of games. Before we start, let me say two things about this notion of a method. Okay, so whether a method is good or not depends on what problem you're trying to use it to solve. Okay, so that's I hope that sounds very reasonable. Right? So sipping and tasting, very good way to tell the difference between wine and water. Very poor way to tell the difference between water and heavy water. Right? And a completely hopeless way of trying to tell whether or not you're a victim of an evil, deceitful genius who actually has your brain in a jar and is providing electrical inputs. Right? Okay, so the fundamental unit of evaluation is going to be a method applied to a concrete problem. Right? We can't expect there to be a single method that could just work on every kind of problem all at once. Okay, so here's an example of a kind of nice, simple problem. Somebody is flipping a coin, and it's either two-headed or one-headed. It's either ordinary with a head on one side and some other thing on the other side, or it's got heads on both sides. This person is flipping the coin and telling you whether the coin comes up heads or tails each time. And you're supposed to decide whether the coin is two-headed or normal. Okay, so here's a bad method. You could just decide to believe that the coin is normal no matter what the sequence of heads and tails is. Okay? Whatever sequence of heads and tails comes up is going to be consistent with this hypothesis that the tail is normal, that the coin is normal. So you could stick with it come what may. But it's a bad method because if the coin is two-headed, you're never going to find out. And intuitively, you should be able to figure out the coin is two-headed because all the tosses are going to come up heads forever, right? That seems like the kind of thing we should be able to learn. Okay, so that was the example of a bad method. Here's a good method. Start out by assuming that the coin is two-headed, and then change your mind to believing it's normal if any of the tosses come up tails. Okay. That method is a good method because no matter which of the two hypotheses is true, there's zero chance in the infinite long run that you'll end up with false beliefs. Okay, that's the kind of guarantee for convergence to the truth that we like. Right? So here's a case, very simple case. Learning is clearly possible. Some methods are good because they lead you to the truth no matter what. And some methods are bad because they don't. Right? That's the whole point of this proposal. Same kind of thing with a loaded die. Okay, so a die is going to be rolled, an ordinary six-sided die, but it's not perfect, it's loaded. It might be perfect, sorry. It might be a chance of exactly 1 in 6 of 6 coming up, or it could be some other number that gives the chance for 6 to come up, as is probably the case with most actual dice. So you're supposed to determine what the chance of 6 coming up on any roll of this die is. And here's a really simple-minded way of doing it. If the die has been thrown n times, let's say 5, and it's come up 6 m times, let's say 2, then you guess that the chance of the die coming up 6 in the future is m over n, so 2 over 5 in our illustration. Right? So you're just like, I just read the answer off of the data in the most simple-minded possible way. That's a good method for this. It's not the most sophisticated possible method, but it has the feature we want, that no matter what the real chance of 6 coming up is, this method will output a sequence of guesses that's basically guaranteed to converge to the true number. Right? So the difference between the true number and the number that you guess is expected to get smaller and smaller as more and more evidence comes in, closer and closer to 0. That is a good method. Okay, so the point about this is The technical point's up there for people who care. I won't talk about it. The point about this is these sort of nice, simple problems are pretty good surrogates for the very simplest kinds of problems that come up in the sciences. And so far, this proposal that we should approve of methods that are convergently objective and disapprove of ones that aren't looks good in the way it handles these kinds of problems. Okay, but here's a kind of problem where things go wrong. Snow days. So nature is presenting us with an infinite binary sequence, okay? Whether we like it or not. Every day, starting, I'm saying, on September 1st, 2010, the beginning of NYU Abu Dhabi, nature decides whether it's going to snow or not in Abu Dhabi, and the administration decides whether or not to cancel classes. Okay, so we get this infinite binary sequence starting on the first day, September 1st, 2010. I assume it was a 0, which means classes were not canceled. And probably on the next day it was also a 0, which means classes were not canceled, and so on. Have there been any days on which classes were canceled due to snow on this campus? Nobody can remember any, so let's say it's been 0 so far. So, you know, that's a few thousand zeros in a row. But we don't know how it's going to continue, right? Sometimes you get a lot of zeros and then you get some ones. The Arabian Peninsula is slowly drifting away from Africa, and who knows where it'll end up. It could end up where Antarctica is now. And I mean, NYU Abu Dhabi is going to go on forever. There may be some snow days in its future. We don't know, right? Even though there have been a lot of zeros so far. But nature and the administration together are presenting you with this infinite binary sequence. And your job is to predict what its future will look like. So every day, you find out whether classes are canceled or not. You have the whole record of whether classes have been canceled or not so far. And then I'm asking you, predict what the rest of the sequence will look like. So here's a couple of forecasting methods for handling this problem, personified. So the first character, Ms. 0, just says, I don't think there's ever going to be any snow days. No matter what the data is so far, I don't think there will be any snow days in the future. So her way of making a forecast is to take the historical record, happens to be all zeros so far, but even if there were some ones in it, she would do the same thing. She takes the historical record, and then she just tacks all zeros on the end of it. And she says, there's my forecast, every day. It's a good system. Mr. Nietzsche thinks history repeats itself. So no matter what the historical record is, his prediction is that that pattern of zeros and ones predicts itself forever. Okay, so these are two different methods of making forecasts. They're both convergently objective. So what does that mean in this case? It means for any day, no matter how far in the future, eventually all their forecasts are right about that day. If you think about it, that's kind of easy to do in this problem. You just have to wait until that day has occurred and make sure you predict what actually occurred on that day. So this is a problem for which convergent objectivity is really easy, even easier than it was in those toy examples. So that's good. Ms. 0 and Mr. Nietzsche are both convergently objective for this problem. Here's a second version of snow days in Abu Dhabi. In this one, in addition to having to forecast what the future is like, you're also asked the following question. Is the probability of a snow day 1 in a million? Okay, so every day you have to say, output your forecast forever, and you also have to say, is the probability of a snow day exactly 1 in a million for all time? Now, Ms. 0 is always going to say no, right? So she always thinks, no matter what's happened so far, it's going to be all zeros in the future. So she thinks, from a certain point on, there's never any more snow days. So definitely not probability of 1 in a million. She thinks the overall probability is 0. So she always says no to this question. Mr. Nietzsche is a little more flexible. He says, well, it depends. Sometimes I say yes, sometimes I say no. So if, when I look at the historical record, there's been exactly 1 snow day for every million days the university's been open, then I expect that pattern to repeat itself forever, so I say yes. But if the historical record has any other frequency of snow days, then I say no, because I expect that to continue forever. Okay, neither of these methods is convergently objective for this version of the problem. They're good at forecasts, but they can't answer the question, is the probability of snow 1 in a million? So just to make this part quick and concrete, let's consider a particular possible sequence of data that we might get. So we agreed the actual sequence starts out with a few thousand zeros. Right? Let's say those zeros continue up until day 1 million, and then there's a snow day. And then it's all zeros up until day 2 million, and then there's a second snow day, and so on. So this is like a very, very simple kind of sequence in which the frequency of snow days is actually 1 in a million. Okay, so if it looks like that, Ms. 0 is obviously not going to converge to the truth, because the actual answer is yes, the frequency of snow days is 1 in a million. But her answers to this question, is the frequency of snow days 1 in a million, is going to be no every day. She's going to say no, 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 forever. And that doesn't converge to yes. Right? There's like an unbridgeable gap there. Mr. Nietzsche is also in trouble. So think about how he starts out. Right? He's like, up till now, it's been a few thousand zeros, so he expects it's all zeros in the future. So up until now, he's been answering this question, is the probability of snow 1 in a million? He's been saying no every day. When he gets to day 1 million, he'll change his mind and say, oh, yes, the probability of snow is 1 in a million. But on day 1 million plus 1, he'll go back to saying no. Right? Because the frequency of snow days in the actual record has dipped just below 1 in a million. And he'll stick with no up until day 2 million, when all of a sudden he looks at the historical record, the frequency of snow days is exactly 1 in a million, and he'll say yes again. And then on day 2 million plus 1, he'll say no. And he'll go on like that. Every million days, he'll say yes. All the other days, he says no. Okay, that sequence doesn't converge to the true answer, yes. In fact, you think it doesn't really converge to anything, right? It's like a sequence that goes 0, 1, 0, 1, 0, 1. That doesn't converge to anything. Same thing with this sequence. It flip-flops forever between yes and no. An infinite number of times. He keeps changing his mind. In order to succeed at this problem, you have to eventually make the right guess and stick with it, because you're just given two choices, yes or no. That's what causes the trouble here. Okay, so more generally, and we can talk about this in the question period if you want to, every method for solving this problem, snow days in Abu Dhabi part 2, every method either has the flaw that Ms. 0 has or the flaw that Mr. Nietzsche has. So either it's closed-minded and it makes up its mind after seeing a finite amount of data, and then it will be fooled by sequences that start that way but then do surprising stuff afterwards. And then it will sometimes it will converge to an answer, but it'll be the wrong one. Right? That's what Ms. 0 did. Or if the method is open-minded, if it never makes up its mind completely, in the sense it's whatever it's saying right now, it's always willing to change its mind if you show it the right data later. If a method is open-minded, then there will be circumstances under which it flip-flops ad infinitum, like Mr. Nietzsche does. And so it won't converge to the right answer either. So for this problem, there's no method that's convergently objective. Okay, so this is a little frustrating, right? We started out with a problem, the first version of snow days. It was easy. It was easy to come up with convergently objective methods. But for this second problem, it turns out it's impossible. And that's frustrating. But it's worse than just frustrating. It's a disaster. So we've been pursuing the suggestion that you should believe the outputs of convergently objective methods, but don't believe the outputs of non-convergently objective methods. Right? That was the proposal we started out with 10 or 15 minutes ago, where we said, yes, that seems so reasonable, let's do that. Right? But look what happens if you do that with this pair of problems and these methods. Ms. 0 and Mr. Nietzsche should both believe their forecasts about the patterns of future snow days, because their methods of making forecasts about the patterns of future snow days are convergently objective. So the proposal says, yes, they should believe those forecasts. But then there are methods for addressing the question of whether the frequency of snow days was going to be 1 in a million, turned out to be not convergently objective, so they shouldn't believe those outputs. Right? So like Ms. Zero will be saying to her friends, I figured out what the pattern of weather is going to be forever. Here's the answer. And they say, is the frequency of snow days going to be 1 in a million? And she says, I have no idea. That's very close to being inconsistent. So imagine Newton had done something like this, right? Newton published a book in which he said the force of a gravitational attraction varies as the inverse of the square of distance between two bodies. And if someone had said, but Sir Isaac, does it also vary, say, inversely as some polynomial between the masses of those two, the distances between those two bodies? He would have said, yes, you fool, of course. I just told you something much stronger. He wasn't very nice. Ms. Zero and Mr. Nietzsche are in this embarrassing position where they're willing to say, yes, I nailed it. I know exactly what the future is going to be like. And then you ask them like some much weaker question, and they have to say, I don't know. Right? A much weaker question about the very same subject matter. Right? If Ms. Nietzsche is totally serious about her forecast about the future, then when you ask her, is the frequency of snow days going to be 1 in a million, she should always say no, because she always thinks, no matter what's happened so far, from now till infinity, it's all no snow days. So the frequency should be 0. Right? She's in the very, very uncomfortable position. So if you endorse this apparently really attractive, beautiful proposal to like approve of methods that are convergently objective and disapprove of methods that aren't, then you inevitably end up in this terrible position of having to say, I believe P, some proposition. And someone says, well, do you believe P or Q, some weaker one? And you're like, I don't know. Okay. From a logical point of view, that is a disaster. So, as reasonable it sounds, the suggestion that we should believe the outputs of convergently objective methods, the ones that are guaranteed to converge to the truth, and doubt the outputs of others has to go. And with it, the most promising idea for drawing the boundary between acceptable and unacceptable preconceptions. Okay, so you have to give up. You can't say, I approve of convergently objective methods and I disapprove of the ones that aren't convergently objective. You've got to, you can't have, that combination won't work. You've got to give up on one or the other or both of those ideas. Okay, so that's, that's our discovery. So that's disappointing. If you're me and you dragged yourself through that discovery, you'd be very disappointed at the end of it, because you would have thought, I have a good idea for trying to solve an intractable philosophical problem. Right? You could sort of see these kinds of methods that we've been talking about today in a more sophisticated form are parts of computer science and statistics. Right? So if this problem feels like it's on the verge of being taken away from philosophy, but it's not. Right? It's permanently intractable, as far as I can tell. Okay, so let's go back to the beginning. Lord Russell, what good is philosophy? You'll remember his first answer was a histrionic sigh. Then he went on, in a part I didn't show you, to say, I think philosophy has 2 uses, really. The first one is it keeps speculation alive. Okay, so despite his emphasis on the importance of science, he thinks there's lots of questions that are very, very interesting that science doesn't care about. Philosophy keeps alive our interest in those. It also keeps alive our spirit of speculation so that we keep working on these intractable problems and coming up with ideas which may or may not one day become scientific ideas. Okay. So that's part of his answer to what good is philosophy. And then there's a second part, and I'll show you the clip to back it up. And it sort of sums up the position that I think I'm leaving you in. So this is the last word.
But there's another use which I think is equally important, which is to show that there are things we thought we knew and don't know. On the one hand, to keep us thinking about things that we may come to know, and on the other hand, to keep us modestly aware of how much that seemed like knowledge isn't knowledge.
Thank you very much. I think I have two questions. I'll ask the first one, depending on your answer. I probably ask the second one, if that's okay with you.
Thank you.
So just now you gave the example of Miss Cyril and Miss Nietzsche, and you made a comparison of that with Isaac Newton saying, imagine, empirically the data shows this, but however, don't ask me a weaker question. And by making that comparison, you're stating that the phenomenon that we just described is a disaster. However, it seems to me maybe it will be great if you can make some clarification whether it is actually the case that in the question that Isaac Newton was asking, those two questions are actually, one of them is stronger than the other, because asking, okay, in some other words, is it possible, could you explain why you think the two questions that Isaac Newton was being asked are not at an equal status, why one of them is stronger than the other?
Yes, okay. So I mean stronger in just in a logical sense. So you could imagine there are all kinds of laws of gravity he could have tried. I think, in fact, he just tried power laws. So he would put r to various exponents and see which ones worked. And r to the second worked and the other ones didn't. He could show that you don't get, in the case where you just have the sun and one planet, you don't get closed orbits if the exponent in the law of gravitation is anything other than 2. So he knew things like that, and so he said, no, it's got to be exactly 2. Okay. So he considered all these possible power laws, and he said, no, it's exactly this one. Now, you could have, so when I say one question is, I say, when Newton says, it's 1 over r squared, what he says is stronger than what he said at the beginning of the investigation when he said, well, it's 1 over r to some power. Right? So because 1 over r squared implies 1 over r to some power, but not vice versa. So when I say stronger, I just mean logically stronger in that sense. If you've got two propositions and one implies the other but not vice versa, then the first one is stronger than the second.
I have a question about this convergence of these two sequences of predictions that they were making. Could you explain again why you say that they both converge to the truth?
Yes. So I can say, let me say very briefly for people who like mathematics, what the answer is. Does that include you? Okay, good. So basically, and then I'll talk to everybody else again in a minute. But for now, let's indulge in some jargon. So our space of hypotheses is the space of infinite binary sequences. Okay, and one of them is the true one that's being presented bit by bit to the agents. And after each bit is presented, and each agent makes a conjecture, which is a point in the space of infinite binary sequences. So we've got the space of infinite binary sequences, we've got a true point, and then each of our two characters is making a sequence of conjectures, which is supposed to converge to the true one. That's what we want. Okay, so what kind of convergence? Well, let's just have a topology. on the space of infinite binary sequences. So we start out with the discrete topology on 0 and 1, because what else, the other topologies you could put on those two bits are bad, right? So we start out with the natural topology on the set 0, 1, and then we take the product topology of 0, take the set 0, 1 with itself, take the infinite product of that, that's the space of binary sequences. The topology there is going to be the topology of pointwise convergence for sequences. So as long as the criterion, and now I can start talking to everybody else again. The criterion for convergence is for each day that occurs somewhere in the future. Sorry, let me say it again. Your sequence of forecasts converges to the truth if and only if, for each day that occurs in the future, for each day that ever occurs, there's some point in time after which your forecasts always nail what happens on that day. And so basically, any method that always begins its forecast with a historical record and continues in any arbitrary way is going to have that kind of pointwise convergence. So it's very, very easy to come up with convergent methods for this problem, but strangely difficult to come up with methods for answering questions about whether the true sequence belongs to a certain kind of subset of the space of sequences, namely one that's dense and has dense complement. You can never have a good method for answering a question like that.
I have two questions, actually. One, I think it would be, it's quite easy. The example you gave of preconception, the Ebola virus image, that's just historically determined, isn't it? I mean, you can only use that.
Yeah.
You can only say that as preconception. It was a preconception to use a microscope before we knew what the Ebola virus is, so that doesn't count anymore.
That's right. I completely agree. I keep doing that. Sorry. Yeah. The point of the slide was to motivate the blank slate picture, and that it shouldn't necessarily apply to each individual inquirer. It could be a historical matter, just like you say.
The other one was slightly related, but when you look at Bertrand Russell was talking at the end of his life there, 90, and so if you go back to his early career when he was still when he was already a philosopher and a great philosopher, say before quantum theory. I mean, there's this presumption by the way he spoke that he would understand everything, and then and so that the remit of his philosophy is always evolving from science, which he understands, because if he doesn't understand it, how does he understand what the philosophy is? So does that mean that he knew and understood quantum physics and relativity and all science in order to be a philosopher?
Yeah. So I mean, Russell, of course, is a very special case. I mean, a person of such tremendous ability and also such tremendous drive. I mean, the amount that he wrote, the number of topics that he wrote about, the amount that he had to do with physics, but also especially with mathematics. I mean, it's sort of astonishing. It's true, though, that I've never read anything by him that showed too much of an engagement with quantum physics. Special relativity, definitely. General relativity, I'm not so sure. I mean, I think, according to this joke that he liked to make near the end of his life that we got in the clip, but you can also find it in many places in print, and sometimes he sort of says explicitly, it's a joke, but it's sort of true, that science is what we know and philosophy is what we don't know. I mean, to the extent that he's serious about that picture, I think he can say, to be a philosopher, you can just focus on the questions that have been left to philosophy because nobody else wants them. But I think you're also totally right that those weren't the only kinds of questions he was interested in. He was also interested in the questions that were living parts of mathematics and physics and psychology. And he thought that he and other philosophers could make real contributions there as well. So yeah, I think even according to Russell, this wasn't the whole story. There's some room for a peculiar skill that he thought philosophers had that allowed them to contribute to even these very specialized sciences.